and if you use the midpoint rule, then over here, and you use the midpoint rule, then you know you're going to be less expert. So certainly your error is going to depend on your n, your delta x, and b minus a. It will depend on these things. What else will it depend on? It will have to depend on the function you have in your hand. You can imagine doing a trapezoidal rule of this function from 2 to 7 versus a trapezoidal rule on this function from 2 to 7. You know you're going to be less accurate here. The function is changing too quickly. And how do we measure how fast a function is changing? The derivative. So if you have an idea about the derivative of this function, then you will be able to estimate the error without knowing the actual integral. I'm not going to go into the details, trust me. This is really a graduate class. But here are the formulas I will give you on the test, but you must know how to use the formulas. The error formulas for the trapezoidal rule. For the midpoint rule. The error formula for the trapezoidal rule and the error formula for the same. Here they are. That's a theorem, which means you have to do some serious analysis to prove it. The error on the midpoint rule is no more than b minus a. So the bigger the b minus a, the bigger your error. Times delta x squared, the bigger your delta x, the bigger your error. Divided by 24 and some constant k. This constant k is a measure of how fast your function is changing. And it is the maximum of the second derivative of your function over the interval you are integrating. So if you're integrating from a to b, you will need to differentiate this function twice and look at the maximum value, and we are all experts on maximums, on that interval. If you know on that interval the second derivative is no more than 5, you can put a 5 here. And for the trapezoidal rule, it will be the same thing. Your error will be no more than b minus a, so the bigger the difference this is, the bigger your error. Divided by 12, delta x squared, the smaller your delta x, the smaller your error. The bigger your delta x, the bigger your error. And again, this constant k is the maximum of the second derivative over the interval a, b. That is an absolute value.
Did you say the constant k was?
Yeah, right here. is a real number such that the second derivative is less than k on the interval AB. In other words, if you can find a bound on the second derivative of your function over the interval AB, you find out that that second derivative is no more than 5. You can put a 5 there. In other words, the function is not accelerating too much. Now, we know that if you are using a linear function, what is the derivative of a linear function? Constant, and what's the derivative of that? So if you are using a midpoint rule on a linear function, you're going to get an exact answer. Because this is going to be 0. Yeah. Now the Simpson's rule is very, very accurate. Your error will be proportional to the width of the interval. The larger the width of your interval, the larger your error. Delta x to the power 4. In other words, if your delta x is 0.01, you're going to do 0.01 times 0.01 times 0.01 times 0.01. Divided by 180, a larger number. And k, which is a bound on the fourth derivative between a and b.
7 over 5 or 6 pages.
Indeed, it is some serious numerical analysis. Now, what is the derivative of x cubed? 3x squared. What's the derivative of 3x squared? 6x. What's the derivative of 6x? 6. What's the derivative of 6?
0.
In other words, if you are using a Simpson's rule on a polynomial of degree 3, the answer is exact. That is to say, if you are trying to approximate this thing here with a Simpson's rule, you are going to get an exact answer. With the Simpson's rule. Quite astonishing. And it doesn't matter how thick your interval is. But the dirty work is here. Bounding your second derivative on the interval a to b, and bounding your fourth derivative on the interval a to b. But that is calculus 1. You will have to differentiate it twice and look at it over the interval a to b. You will have to differentiate it 4 times and look at it over the interval a to b. And I'm going to ask you calculus 1 professor. What's the maximum of this function over the interval? Maximum is either at the endpoints or at a critical point. So you will check the second derivative at a, you will check the second derivative at b, and you will check the second derivative at the local maximum and local minimum. If you had to do calculus 1 professor, that is. You will check the fourth derivative at a, you will check the b, and you will check the fourth derivative at its local maximum and local minimum.
So taking the derivative again.
Well, if you want to maximize. Huh? So, and by the way, that is one way to use these formulas. Another way to use these formulas is to say, how many steps do I need to be within this tolerance? That is to say, if you want your error to be less than this, or if you want your error to be less than this, which one is going to need more steps? Question. This will answer exactly how many steps you need. That is to say, the n is coming in here. So you will put your error here, you will put your b minus a here, you will put your fourth derivative here, and you will try to solve it. these relationships. So we're going to do this both ways. We're going to say, well, here is the Simpson's rule with n equal to 4. I don't know what the exact integral is. Here's my approximation. How accurate is my approximation? Or here is a function integrated from 2 to 11, and I want the error to be no more than 0.05. How many steps do I need? So that's another way to do this. Let me do the Simpson's rule on the quiz. All of them. I'll tell you the error. On all of them, I'm going to apply this analysis. I remember on the quiz we approximated this integral. We did the trapezoidal rule, we did the midpoint rule, and we did the Simpson's rule where n was equal to 4, and our delta x was what was our midpoint rule approximation?
0.38.
I'm sorry? Someone write it down, the midpoint approximation.
388.
The midpoint? The trapezoidal?
0.3834.
388.34. 86. We don't know the exact answer. We want to know how accurate it is. So, I'm going to use these. The